Good afternoon. So let us start today's lesson. We talked about number sequences. It is in the same chapter as number theory, but it is not related to number theory in principle. But that's also an important topic in its own right. Yes. So what do we mean by a sequence of numbers? It is clear that you have a list of numbers, but that is important for you to understand that this is an ordered list. Yes. So for example, if I have, let me just write, the most famous sequence ever is probably the sequence of numbers that you can just count with them. 1, 2, 3, 4, 5, and etc. If the sequence continues forever, that is called an infinite sequence. But if it stops somewhere after writing some of the, then that would be a finite sequence. Each one of these numbers that you see that appears here is called a term of the sequence. Yes? For example, I can use letter A to indicate this sequence. Yes? Then this sequence A consists of these numbers in this list. Number 1 is called the first term of this sequence, and it is denoted by A with a lower index 1. This means the first term of the sequence whose name is A. And then this one, in this way you can denote it by A sub 2. It means that the second term of the sequence whose name is little a, and etc. etc. So that is a sequence. But what is important for you to understand is that if I interchange, for example, between this 1 and 2, and I write 2, 1, and then I keep this everything the same, this sequence and that sequence are not the same by definition. So sequence is an ordered list of numbers. So if this sequence is called A, I call this sequence to be B, then the sequence A is not equal to B by definition. So that's one thing that I want you to know, that when you have a sequence of numbers, you need to respect the order in which the numbers appear in your list. Yes? So here, for example, if I ask you what is B1, B1 means the first term of the sequence called B, which is 2 in this case, and what is B2? B2 is 1. So you see that B1 is not equal to A1, B2 is not equal to B2, even though the rest of the elements in that sequence, or the terms is better, elements is for sen. Then the rest of the terms are exactly identical. But these two sequences are not considered to be the same. So that is what I want you to know. The second thing is, so this number that you see here, I will call it a counter. So it counts the elements, the first element, the second element, the third element, and etc. It is clear by its definition that the counter is a natural number, yes? Some books, they start from A sub 0 because they are considering the set of natural numbers is starting from 0. Okay, in that case, you can also allow for 0. But usually, of course, in some books you see that, but usually it doesn't make sense to write A sub minus 2, yes? It is the negative second term of this sequence, which doesn't make sense. So the counter should be actually a natural number. But this is not the case for the term itself, yes? Of course, in this case, what I have written, everything is a natural number, but I can introduce you a new sequence. For example, I can write 1, I can write 1 over 2, the next one 1 over 3, the next one 1 over 4, etc., etc. Okay, so if I ask you what is C sub 1, first term is 1 again, but the second term is 1/2, the third term is 1/3, and etc., etc. Yes? So you see that still the counter is a natural number, but the term itself is not a natural number in general. Yes? Is that clear? So the numbers that appear in your list could be any numbers from the set of real numbers in our course, or even set of complex numbers, which we don't want to discuss about. And of course, in these examples that I have written so far, I am following some kind of nice pattern. There is no reason that there is a pattern going on. It could be completely random numbers, yes? For example, I can have 1, then suddenly the next one can be square root of 2, the next one can be pi, I don't know, the next one can be pi to the power of e, the next one would be square root of 2 plus square root of 3, and etc. Of course, then this etc. doesn't make sense, yes, because we don't know what's coming next, because there is no pattern. So this etc., these 3 dots, when I use, it means that if you follow the sequence up to that point, it is naturally easy to guess the next one. Otherwise, I'm not allowed to use these dots. For example, here these dots doesn't clear. But still, if I tell you, is this a sequence? I would say yes, that's still a sequence of numbers. Yes. Is that clear? Okay. But of course, we cannot say anything specific about these sequences. So we can just rule them out. We don't. Of course, these are sequences, but we cannot say something about them. For example, what do I mean by saying something about them? For example, if I ask you, what is the term number 1000 here? You can immediately answer that. That is 1000. If I ask you, what is the term 100 here? What is that? Yes?
1 over 100.
1 over 100, okay? But if I ask you, what is the I don't know, what is the 10th term here? You cannot answer because there is no pattern, yes? So usually we exclude these things, even though they are technically sequences. Okay, and then if I can write a formula so that using that formula I can generate all the terms in my sequence, that is called the general term, yes? So, for example, in this case, what is the general term? Can you write a formula so that let me just explain it here. By formula I mean here, so you can write the nth term is equal to n, yes? Is that understandable? Because if I replace this n with 1, I will generate the first term. If I replace n with 2, I will generate the second term. And it is clear that if I replace n with consecutive values, natural values for n, I will generate the rest of the sequence. So there are 2 names for this. You can call it the nth term, or you can call it the general term, yes? And it is not always easy to find the general term, yes? Even if you are following a good pattern. So for example, so can you guess what is the nth term of this sequence that I am writing? Yeah, I think it's enough. So this is a sequence. This is the first term, the second term, the third term, etc. And it is apparently following a nice pattern. So for example, you can immediately guess what is coming next. What is coming next?
6 over 7.
Yeah, so when you can guess what is coming next, I am allowed to use these dots, yes? But what would be the general formula? So let me call this sequence S. Then what can I write for S sub n, meaning the nth term or the general term of this sequence? So it means that you need to write a formula in terms of n so that replacing n with natural values will generate these terms one by one without ignoring one of them. Yes?
n divided by n plus 1.
N divided by n plus 1. Yes? Why is that? Because if I replace n with the first natural number 1, then it will generate 1 over 2. Then when I replace it with 2, it generates the second one, and etc. Do you think that I could also write this? Do you agree that this is correct? Yes or no? Yes, Dimitri?
No,
Why not?
because if n is 1,
Yeah.
it's going to be 2 divided by 2.
Yes, so it means that this is more or less correct, but it is not generating the first term. It generates everything after the second term onwards, yes? Because the lowest value for n, let us have this convention, I always start with the lowest value 1, not 0. And then it means that when I put 1 here, it will generate 2 over 3, which is this term. When I put 2, it becomes 3 over 4, which is the next term. And it will start generating every one of these terms one by one, but not the first one. So this one is not the general formula for this sequence. On the other hand, if I have started from here, this is not the general formula for this sequence. This would be the correct one. But for this case, I have to take this away. Questions? Is that clear? So you have to generate every single term from the first term. Yes? Okay. But of course, this is usually, I don't know, have you seen some IQ tests or something like that? There are some numbers, you are supposed to guess the next one. It depends how well it is designed. So this is not part of our studies. Yes? For example, can you guess can you find a general formula for this? So I would say that I will start with 1. The next one would be 2. The next one would be 4. The next one would be 7. The next one would be 11. The next one would be 16, and etc. Of course, IQ tests are easier than what we were going to do. So here, I think you can guess the next one. So what's the next one? 22. Yes? So it is 22 because you see that, at least you can see this pattern. 1 is added. And the next one, how much is added?
2.
And the next one? 3. And apparently, if this is going to be a nice pattern, so the next one should be, so it becomes 20. Yes? So this is an easy question. But the harder question is that find a general formula now. Can you find a formula that generates these numbers one by one? Okay, I want to pause the video and I want to give you a little bit of time so that you can think. Any guess for the formula? Okay, I can wait a little bit more. Okay, so what's the answer? What is the answer?
Is there a method?
Yeah, that's a good question. Is there a method to find that? The general answer is not easy. So in general, it is not easy to follow a very prescribed way of doing this. Yes, sometimes we cannot find it. But I don't know, if you have a guess, I can check your guess, but probably we can still discover, here we can do some systematic work here. Okay, can you guess what we can do at least? If you cannot guess, but probably you should be able to guess where we can start from, because the pattern is clear. It's not a very complicated pattern, yes? It's a very simple pattern. So, but still you see that it's a little bit hard to discover the correct formula for generating this one. So my question is that, if we call this the sequence T, my question is that, what is T sub n in terms of n? You don't have the formula? Okay, but let us try to discover that. Yeah, this might need a little bit of something that I will study later, but I think you can do it because you have seen it in Math 1C as well, I think. So, what I see that what is happening, each term, so can you tell me, so the second term minus the first term is how much? Is how much? 1. The second term, the third term minus the second term is how much? Is 2. Yes? And then I don't know, the fourth term minus the third term is 3. So if I continue this, the nth term that I am looking for minus the previous term. How should I write it mathematically? What is the previous term? Yes, t sub n minus 1 appears as the index. Yes? This is how much? Can you tell me? No? Just look at the pattern. N minus 1. It's n minus 1, not n. Because when it was t2 minus t1, it was 1. When it was t3 minus t2, it was 2. When it is t4 minus t3, it is 3. So when it is t sub n minus t sub n minus 1, it should be n minus 1. Yes or no?
Yes.
Is that understandable? Do you have any idea? But my question is just only for the last one. Of course, I know these things, but the point is that I am not supposed to write everything up to this point to find the pattern. So what can I do? I can add them. Yes? If I start adding them, something nice happens. This is called a telescopic sum. A telescope, you know that it will actually collapse into itself. So this sum is also the same thing. Why? Because when I start adding them, this will cancel that one. This will cancel that one. This will be cancelled by the next one. And when you come here, which one is left? This one is cancelled with the previous one. Agree?
Yes.
Okay? So, and then from this list, what is left for me is t sub n from the last one minus t sub 1 from the first one. Yes? Yes or no? Yeah? And then the right hand side I have to add them. So it becomes what? 1 plus 2 plus 3 plus up to plus n minus 1. But what is t1? t1 is 1 in your list. So this becomes tn minus 1 is equal to 1 plus 2 plus 3 plus up to what? N minus 1. Agree? Then I move this 1 to the right hand side because I am supposed to find tn. But I can write 1, 2, 3 up to what? N. And that is the famous formula. I don't know if you remember it from Math 1C or not, but of course I will teach you this again this year. But this is a famous formula. It's n times n plus 1 divided by 2. So that was the formula probably you were not able to guess. It was n times n plus 1 divided by 2. Let us check. If I put n equals to 1, what it generates? It generates 1. If I put 2, 2 times 3 divided by 2 is what? Oops.
It's minus.
It's n.
No, I made a mistake probably in my calculation somewhere.
Yeah, it's n times n minus 1 divided by 2 plus 1.
Oh.
No, but yes, you are right. The formula that I have written for this one is correct, but I have done something wrong here. Yes, that was right. That was my mistake, sorry. So let me do it like this. Tn minus 1. This formula is n minus 1 times n divided by 2. Then I move 1 to the right hand side. So it should work, I don't know. Yeah, so it is n minus 1 divided by 2. Sorry, yeah, I think I did it very fast. So this is the correct one. Yes? This is the correct one. So I made a mistake. So yes, that's the correct formula. I mistakenly take minus 1 here and cancel that minus 1, which is not possible. Okay, so this is the correct formula. Let us check. If I put n equals to 1, 1 times 0 divided by 2 is 0 plus 1 is 1. So that's correct. If I put n equals to 2, 2 times 1 divided by 2 is 1. 1 plus 1 is 2. If I put n equals to 3, 3 times 2 divided by 2 is 3. 3 plus 1 is 4. And let me check once more. If I put 4, 4 times 3, 12 divided by 2, 6. 6 plus 1, 7. So that will generate this sequence. Is that right? So, but I think you see that in principle, there is no general method if the sequence becomes complicated. Okay? But I want you to understand, it is not that easy to find the general formula for any sequence if actually there exists a general formula. But in this case, we were able to do that. Of course, the reason that we could do it because we knew about this sum. If this sum is more complicated, we don't have any formula for that, then we will be stuck there, yes? But anyway, for this case, we were able to generate that formula a little bit systematically, yes? Is that clear? Okay. So the best way to define a sequence is to giving the general formula. It's more compact and convenient. I can, of course, list my sequence, but the point is that in this question, if you didn't know about the general formula, if I ask you what is the term number 100, you can do it, but you have to do it step by step to reach to the 100th term. But if I ask you here, you can immediately answer. So this is the benefit of having the general formula for a sequence if there is one. So here, if I ask you what is the term number 100 in this sequence, then you can just put 100 there. So it becomes 100 multiplied by 99 divided by 2 plus 1. And then, I don't know, you calculate this one, how much is that? 4,950, is that right? Plus 1. I don't know. So this one is 9,900. And if you divide it by 2, yeah, that's correct. I think that's correct. Anyway, you can calculate and find the number, yes? So you see that if I have the general formula, it is easy to answer questions regarding the sequence, yes? But of course, the bad news is that this is not always possible, or at least for many of the sequences, it's not possible, yes? For example, let me give you, this is, by the way, it's not easy at all, but there is a famous sequence called the Fibonacci sequence. So Fibonacci sequence, yes. There are different versions of Fibonacci sequence, but I want to start with one. I will write this one. I know that you can guess the next one. So 1, 1, and then the other one 2, the other one 3, the other one 5, the other one 8, the other one is 13. What is the next one?
21.
It's 21, yes? Because here I have two terms, 1. I add these two, it becomes the next one. I add these two, it becomes the next one. I add these two, I add these two. So the next one is 21. But now, can you guess the general formula for Fibonacci sequence? Is the question clear? The same question as before. I have a nice pattern of numbers. It is a nice pattern because you can guess what comes next. Yes, what's coming next? 34. What's coming next? You can just 55. Right? You can do that. So it's a nice pattern, exactly like the pattern that we had here. But here we could immediately calculate. Immediately no, but it was not hard to find the formula. We want to do the same thing here. What does it mean? Let me call Fibonacci for f, capital F. I want to find a formula for f sub n. Okay, so this is one of the hard problems actually. So the formula turns out to be this formula. The numbers appearing in the formula are strange, yes. So so to learn how you can do this, we can prove it, by the way, after we learn mathematical induction. So it means that someone should generate this formula give it to us, then we can prove that yes, this is correct mathematically. But how to generate this formula? This is a very strange formula, yes? Because here we have some natural numbers. In our formula, we also have natural numbers involved. 2, 1, and something like that. But here, even though I have natural numbers, then I have irrational numbers involved. And then it is very interesting. We are claiming that this very complicated formula will generate this sequence one by one without having one square sign left. Yes? So I want to tell you that I didn't expect you to find this formula. I wanted to see that this might be sometimes hard, yes? But if you don't believe, let us at least check that this will generate the formula, these numbers, okay? I hope that I have written it right. And by the way, there is this number is ubiquitous in mathematics, and that is called the golden ratio. You can read a little bit about the golden ratio on Google. I think it's good. And this is the reciprocal of this number. Why is that? So this number has a specific name. It's called the golden ratio, and it is denoted in math literature by phi. It's a Greek letter. So it's 1 plus the square root of 5 divided by 2. So let me calculate 1 over phi. What is 1 over phi? So 1 over phi is 1 over 1 plus the square root of 5 over 2. So it becomes 2 over 1 plus the square root of 5. I am claiming that this number you see here is 1 over phi. Why is that? Why is that the case? Hopefully I haven't done any mistakes. Can you see? This is golden ratio, the golden ratio. The golden ratio, and I am calculating the reciprocal of the golden ratio, 1 over that, which is this one. But then the point is that to rescale it by the conjugate of the denominator. That's a standard technique. Yes? And then what happens? It becomes 2 times 1 minus the square root of 5. And then what do you have in the denominator? So it is 1 minus 5. Is that right? So that's not exactly the number. No, so I was stupid, I think. Why I was stupid? Because this number is negative. This number is positive. So the reciprocal of a positive number should be a positive number. So I shouldn't trust my memory. This is this one. Of course, here it doesn't matter, but here it matters, yes? And then you see what happens. This becomes 2, 1 minus the square root of 5, and then this becomes minus 4. 2 and minus 4 are simplified. I put the minus sign here and flip these two, so it becomes this one. So if I write it in this way, then I am right. But I don't know if the formula is correct, because when I have it, let me check it on Google. I have it the other way around in my memory, but I don't know. What I have in my memory is right, apparently, according to Wikipedia. They are starting from 0. They are starting the sequence from 0. Okay, so might be there are some minor things. If I put n equals to 1, what this formula will generate for you? I think this formula is correct, okay. But I just want to mention, if this is phi, this is 1 over phi. Are you convinced? If this part is phi, this is nothing except 1 over phi. So if I want to write it, if I am right, I don't know, we can test it a little bit. If I am right, the general formula for the Fibonacci sequence that you see on the board is phi to the power of n minus 1 over phi to the power of n, where phi is the golden ratio. Yes? But let us check it. I don't know if that's correct. Let us check. Can you calculate F1 using this formula? Let me not distract you to take these things which are not necessary away. So if my formula that I have written here is correct, if this formula, not my formula, if this formula is correct, then F1 using this formula should generate 1. Yes? Let us see if it is true or false. If I want to calculate F1, it means that I have to replace n with 1 everywhere. So it becomes 1 over. No, I know that this will not generate. That is a bad... I knew that this should be the other way around. Okay, so forget about this. Let me fix it. I should trust my memory. Okay, forget about this. This should be 1 minus the square root of 5. This is 1 plus the square root of 5. And what I have mentioned here, forget about it. Okay. So now let me check this one. What is F1? F1 is 1 over the square root of 5. And then I have 1 plus the square root of 5 divided by 2 minus 1 minus the square root of 5 divided by 2. Agree? This formula is the formula that I have it in my memory, okay? For the Fibonacci sequence. So F1 using this formula becomes this. Agree? And let me calculate. I multiply this minus sign here, it becomes minus 1. It will cancel that minus sign. This minus sign will be multiplied here. It becomes positive square root of 5. Positive square root of 5. It becomes 2 square root of 5. 1 over square root of 5. 2 square root of 5 divided by 2. Yes? And then this one and that one, this one and that one are cancelled, so it becomes 1. So that is right. F sub 1 is 1. But we should also, I hope that this is correct, we calculate f of 2. If this formula is correct, f of 2 should be 1. It's a little bit more strange, yes? So what is f of 1? F of 2, sorry. F of 2 is 1 over square root of 5. And then you have 1 plus square root of 5 divided by 2 to the power of 2 minus 1 minus the square root of 5 divided by 2 to the power of 2. At this stage that you are doing math 5, this should be an easy exercise for you to find the exact value. So what should I do? I will continue and I would write it 1 over square root of 5. And then I want to raise it to power 2. So what should I do? The denominator to power 2, 4. The numerator to power 2 is the squaring pattern. The first one to the 2, the second one to the 2 is 6. 2 times the first one times the second one. And here, the same story, yes? Do you agree? And now let us do it in our head. This minus 6 and 6 are gone. 2 square root of 5. 2 square root of 5 is 4 square root of 5. 4 and 4 is gone. Square root of 5 square root of 5 gone is 1. So it was very counterintuitive, to be honest, yes? So this formula will generate this sequence one by one. Let us check F3. I don't know, can you calculate F3? Yes? Let us calculate F3. The F3 is already a mess. Yes, because it becomes 1 over square root of 5. Then this to the power of 3, which becomes 1 square root of 5 to the power of 3 divided by 8. Minus 1 minus the square root of 5 to the power of 3 divided by 8. Do you think this number is just the innocent number 2 or no? How should I calculate this? Exactly. I want to exactly calculate this expression. So if you don't mind, let me factor a 1 over 8 out and put it here for simplicity. And then, I don't know how many of you have seen these two formulas. Always they are on the formula sheet, do you know? But never people care about them. Yes? Oops. plus 3ab squared minus b cubed. So these are the two formulas that you always see them in the formula sheet, but probably never use them. But now let us use them here. I will give the role of a to this number, give the role of b to this number, and then I raise it to power 3 according to that formula. The first one to the 3 is 1. 3 times the first one squared times the second one is 3 square root of 5. 3 times the first one, the second one squared. The second one squared is 5 multiplied by 3, 15. And then finally this one to power 3. What is this one to power 3, everyone? Square root of 5 to the power 3? You should try if you cannot answer. Yes? 5 square root of 5, yes? Square root of 5 to the power of 3 is what? Square root of 5 to the power of 2 times square root of 5. This is 5 square root of 5, yes? So this is good. So this becomes 5 square root of 5. And then I have no denominators because I put 8 here. And the same thing happens here, but of course, these signs are alternatingly positive and negative, but because I have a negative sign behind everything, this would be different. So this one is positive. Because of this minus sign, it becomes negative. This one is negative. Because of that minus sign, it becomes positive. And the next one becomes negative. The next one becomes positive. Yes? And now let us calculate. This minus 1 and that one are gone. Yes? This minus 15 and that 15 are gone. 5 plus 3 is 8, plus 5, 13, plus that is 16. Yes? So this becomes 16 square root of 5, and then it's a miracle, isn't it? And then this becomes 2. Yes? But then you can imagine that if I go to power 4, you run out of formulas, yes? Because, of course, we will study that. That's called the Newton binomials theorem. So it tells you that how you can calculate if you have 4th power, 5th power, and etc. But I think it's really counterintuitive that these third signs are by miracle they are actually cancelled. And then you get these terms one by one. Yes? So, but this is not the purpose of this teaching. I just want to tell you that even if you have a nice sequence with a nice pattern, finding the general formula can be extremely hard. Yes? Is that clear? And if you can guess one sequence in the world, then you will get $1 million immediately. So if you can find the general formula for the sequence of prime numbers. If you can generate a formula, if you can find a formula that generates the prime numbers one after the other, you immediately get $1 million, and then of course more than that you become probably a very famous scientist in the world. Yes. So no one has discovered that formula yet, because prime numbers, even though we know a lot about them, but they behave very strange. Yes? Okay, so I just want you to have these ideas. So, but here we don't need to be worried about these hard problems, but I want you to see them at least once when you are dealing with these sequences. Yes? Any questions? Okay. Okay. Before leaving the topic of the sequence, because we only deal with two types of sequences. One of them is called arithmetic progression, and the other one is called geometric progression. And they are very, very simple, by the way. We can go very fast. Okay? So, before leaving this section about sequences, there is another way of defining a sequence. It is not as efficient as having the general formula, but it is better than nothing. And that is called recursive relation, recursive definition. So what do I mean by recursive definition? So do you remember I talked about this sequence we just right now? We just found the general formula for this, yes? what was the next one? 16, and then we guess that the next one is 22, etc. So yes, this is a sequence. Even though finding the general formula was not that easy in the first place, but finding the relation between consecutive terms was very simple, yes?
Yeah.
I realized that each term minus its previous term is what? Is n minus 1. Agree? Okay, so this is not the general formula, because if I move this right now to the right hand side, Tn is Tn minus 1 plus n minus 1. This, I cannot write this and claim that this is the general formula, because the general formula on the left hand side you have Tn, but on the right hand side you have to have something only in terms of n. But this is in terms of n and something else in the sequence. So this is called a recursive definition. Yes? So it does not define the sequence for you straight away, but it defines your sequence in terms of one of the previous terms. Yes? So here, if I ask you what is t number 5, you cannot immediately answer it, but still you can answer it. If I ask you what is t5, you replace n with 5, it becomes what? t4 plus 4. But this is not done yet because t4 is not known. Then you use the same formula to calculate things recursively. Yes? So I replace n with 4. It becomes t4 is t3 plus what? 3. But it is not done yet because I don't know t3. But I use the same formula once more. So this becomes t2 plus 2. I don't know t2. I use the formula once more. It becomes t1 plus 1. So you see, if I want to define this recursively, I cannot answer t5 directly. If to answer t5, I need to know t4. To answer t4, I need to know t3. To answer t3, I need to know t2. For t2, I need to know t1. If the people who have designed this question, they don't give me t1, I cannot answer this question. But if they give me t1, for example, say that t1 is 1, in this sequence, then I put it here, t2 becomes 2, I put it here, t3 becomes 4, I put it here, becomes 6, I put it here, I made a mistake somewhere, yes. If t1 is 1, t2 is 2, 4, yes, t1 is 2, sorry, t1 is 1, t2 becomes 2, and I put it here, t3 becomes 4, 7, yes, 11. That's correct. But if they changed, they say that t1 is negative 5, and I can calculate t5 again. But I have to replace t1 with minus 5, t2 becomes minus 4, I put it here, I get minus 2, I put it here, it becomes 1, I put it here, it becomes 5. So this is the way of defining a sequence recursively. So it means that instead of writing the general term in terms of n, you write the general term in terms of one or more previous terms. Is that understandable? For example, can you write the Fibonacci sequence recursively, even though finding the general formula for the Fibonacci sequence was probably very out of reach, but this one, finding the recursive relation is not. Can you write the recursive relation for Fibonacci sequence? So the Fibonacci sequence is this sequence. 1, 1, 2, 3, 5, 8, 13, 21, etc. Yes? Can you write it recursively? What do I mean recursively? I mean, can you write a formula that relates f of n to 1 or 2 or 3 or more previous terms? What is this one? Fn is equal to what?
Fn minus 1 plus Fn minus 2.
That's it, yes? But this is not enough. I need 2 extra pieces of information. So first of all, you need to tell me that this formula is valid if n is greater than or equal to 3. Yes? Because if n is equal to 2, it doesn't work. If I put 2 here, it becomes f of 0. If I put n equals to 1, it becomes f of minus 1, which is meaningless. So, but this doesn't, this in its own does not define the Fibonacci sequence. Because we need a starting point, yes? This only tells you that if you are interested in the nth term, then it is the previous term plus the previous term. But you need a starting point. So I need to give you 2 pieces of information more than this. I need to tell you that f1 is 1. I need to tell you f2 is also 1. So then this means that this is the way that I can define the Fibonacci sequence very straightforward. This is very simple. In contrast to the previous one, which is actually very hard to come up with. Yes? Is that understandable? So that is called the recursive definition of any sequence. It is not that efficient, but it is better than nothing. Yes? At least we have some pattern going on. Is that clear? Yes or no? Okay. Now, after this one, we want to talk about 2 particular sequences. I don't know why you have to repeat it again in Math 5, but let me just try to solve a little bit harder problems this time, yes? So now the title of the lesson would be Arithmetic Sequence. Arithmetic Sequence. In this case, when you say arithmetic sequence, by the way, it means that it contains infinitely many terms. But when you say arithmetic progression, this usually is used for finite. This is usually used for infinite. Yes, but yeah. Might be we can use them interchangeably, I don't know. But usually when you talk about arithmetic progressions, it means that you have a finitely many elements in your sequence. But when you usually use the word sequence, it means that it will continue forever. Okay, do you remember what is arithmetic progression from your Math 1C studies? What is that? Arithmetic sequence or arithmetic progression is a sequence of numbers in which each term is determined from the previous term by adding a constant number to it all the time, yes? So for example, this is an arithmetic progression, yes? So the simplest arithmetic progression is probably 1, 2, 3, 4, 5, etc. up to n. This, what you see here, is an arithmetic progression. Yes, why? Because every time I am adding 1 to it. Yes? This number that I am constantly adding is called the common difference. These words you need to know. The common difference. And it is denoted by D. Common difference can be any number that you like, even negative numbers. For example, I start from here and I write this arithmetic progression. -2, -9, -16, etc., etc. This is also an arithmetic progression. But if I ask you what is the common difference, what is the common difference here? From here to here, how much I am adding? -7. And then you see that I am adding the same -7 here, -7 here. So here the common difference is a negative number. Okay? Common difference can be any number, but usually we consider that the common difference is not 0. Not because it is not possible, because it is not something, it's not generating something interesting. If the common difference is 0, then if I start, I don't know, from 1, 10, for example, from 10, and I will end up always with 10. Okay, so that is also a sequence called a constant sequence. This constant sequence is actually not very interesting for us. For example, if I ask you what is the term number 1000 of this sequence, you can immediately answer. And if I ask you what is the sum of the first 10 elements of this becomes 10 times 10 is 100, yes? So that's not interesting. But except for 0, which is not the interesting case, we consider that every number is acceptable for D. So do you agree that this formula is correct? If Tn is an arithmetic progression, I can write T sub n minus T sub n minus 1 is what? Yes? So that is the definition of arithmetic sequence. There are two questions that we want to answer, both for arithmetic progression and later for another type of progression, geometric progression. That is, we want to find the general term and we want to find the sum of the terms from the first term up to some point. These two questions we want to answer. Okay, so the first question is that I have a arithmetic progression T1, T2, T3 up to T number n, and if it is a sequence it can continue. I give you T1 and I give you the common difference. My question is that what is Tn, and my question is that what is Sn. Okay, Tn is the nth term, Sn means the sum of the terms from the first term up to the nth term, yes? So Sn is defined to be T1 plus T2 plus up to Tn. We want to find a formula for this, a formula for that. Okay, formula for Tn is, I think, very simple. You can also discover it yourself. What is Tn? So, if this is arithmetic progression with common difference D, T1 is actually T1, but T2 is the previous term plus one common difference. What is T3? T3 is the previous term plus another common difference, but T2 itself is this one, so this becomes T1 plus D plus another D. So it becomes T1 plus 2D. And if I, for example, if I want to calculate T4, T4 is T3 plus D, but T3 is this number, so it becomes T1 plus 2D plus another D, so it becomes T1 plus 3D. I think you can immediately guess what will happen for Tn. Of course, if you want to prove it mathematically, you have to use mathematical induction that we will study later, but this is so simple, we don't want to be concerned about that. So what is the formula for Tn? Yes?
T1 plus n minus
1 times D, yes? Because here, this is T1 plus 0D. If this is 1, this is 0. If this is 2, this is 1. If this is 3, this is 2. If this is 4, this is 3. So if this is n, this coefficient should be n minus 1. And you see that T1 is common here, 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 here. So this would be T1, and then I have a D. So this formula you will get in the formula sheet, but you need to know how to use it. So this is the nth term of the arithmetic progression. So if you give me T1, and if you give me the common difference, I can immediately calculate the nth term, yes? I think the questions are very simple, yes? And now, finding Sn is more interesting. So how do you think I can find Sn? How can I find Sn? I don't want to actually give a lot of examples for this lesson because you have already studied them and I know that you can do that. So to just solve some problems in the book. I can give you more harder examples, but let us finalize this here. How can I find the formula for Sn? For example, if I give you an arithmetic, simplest arithmetic progression ever, 1, 2, 3, 4, up to n. I ask you to find a closed formula. Let me tell you what is the meaning of closed. A closed formula means that write a formula which is equal to this one and does not contain these dots. It's a compact closed formula. How can I find Sn? Of course, you already know what is the answer for Sn. That's a famous one. But how can I find Sn? Find a formula for Sn. I don't know, have you seen that before or not? So if I continue this one, so I reach to n minus 1, the next one would be n. I want to find a formula for this Sn that you see on the board. The trick actually, a German mathematician, Gauss actually, is a story that he were able to calculate this immediately by writing this the other way around. Yes? So he wrote that if I want to add this from 1 to n, it doesn't matter if I add it from n to 1. Yes? So it becomes n plus n minus 1 plus up to 2 plus 1. And then he adds them side by side. He adds them side by side. Sn by Sn becomes 2 to Sn. But here 1 and n becomes n plus 1. The next one is 2, but this one is n minus 1. When I add them, it becomes another n plus 1. The next one is n minus 2 here, but this one is 3. When I add them, it becomes again n plus 1. And if I continue this list, when I reach here, when I add them, it becomes another n plus 1. And when I add these two, it becomes n plus 1 again. Yes? So you see that I have all of them the same. How many terms are involved? How many summands I have? How many of them? How many of them do I have? N. Because I have 1, 2, 3 up to n. So I have n summands. But all the summands are the same number and I'm adding them n times. So this means 2Sn is equal to n times n plus 1. And then I divide by 2 and I get my formula. So that is the very, very famous formula. I think it deserves to memorize that. So yes? But of course, this is a very particular arithmetic sequence. What happens if I have the general arithmetic progression? Then how should I do that? It turns out that the trick is exactly the same. It's very nice that we can use the same trick to calculate the general formula. So let us discover that. Okay, so what do I do? Let me write Sn is equal to T1, T2. Let me be clear for writing 3 from the beginning, 3 from the last. Final term. So it becomes Tn here. The previous term is Tn minus 1. The previous term is Tn minus 2. Yes? I want to find a formula for this sum. I do the same trick. I write Sn, but this time I add it upside down. So it becomes Tn here. The next one is Tn minus 1. The next one is Tn minus 2. And then I continue my list until I reach here, T3, T2, and T1. Yes? And then I add them side by side. So it becomes 2Sn. But these two, I add them together. So it becomes T1 plus Tn. I add these two together. So it becomes T2 plus Tn minus 1. And then I add these two, it becomes T3 plus Tn minus 2. Okay, and then I will continue this list. This becomes Tn minus 2 plus T3. This becomes Tn minus 1 plus T2. And finally, I have Tn plus T1. Yes? there is a difference between this one apparently and the previous one. In the previous one, when I add them term by term, I get the same value. But here, do I get the same value? Apparently not. The first pair is the sum of T1, the first term, and the last term. The second pair of brackets contains the second term and the term previous to the last term. So this pair of brackets apparently is not equal to this pair of brackets, is not equal to this pair of brackets. But then what can I do? Yes?
And then don't they become, the D will cancel out and they will become, like you write T2 as T1 plus D, and Tn minus 1 as Tn minus D. And then when you add them, the D's will cancel off and then you just get T1 plus Tn again.
Yes. So in principle, you are proving that even though they are apparently different, but if you look them closely, they are all the same. Yes? That is a very nice argument. So let me follow yours. Yes? So here, T1 plus T1, T1 plus Tn is just the same T1 plus Tn, so forget about this. But here, instead of T2, what can I write? I can write T1 plus D. Instead of Tn minus 1, I can write Tn minus D. Is that understandable? Because T2 is the next term, so I have to add D to T1 to get T2. But Tn minus 1 is the previous term, the term before that. So I have to subtract D from it. Is that understandable? So if you tell me what is this, I will tell you that this is just T2. If you tell me what is this, I will tell that this is Tn minus 1. So, and then the good point is that this minus D and D cancel out, and then what is left for me is again the same content. Yes? And then hopefully you agree with me that this argument can go until the very last one. Yes? For example, for this one, what should I write? Can you tell me? T3 plus Tn minus 2. What should I write for T3? I want to write T1, but how many D's more? 2 D's more. But for this one, what should I write? Tn minus 2 D's. Yes? And then what happens? Again, these two are cancelled. I am left with the same content, T1 plus Tn. So even though they are apparently different, but if you see that all of these pairs of brackets are the same. So instead of this one, I can write T1 plus Tn. Instead of this one, I can write T1 plus Tn. And then I can write T1 plus Tn, T1 plus Tn, and so on. But I have the same summands again. All of them are T1 plus Tn. So how many of them are there? Exactly n of them. So this means that, let me write it here, 2Sn is equal to n times T1 plus Tn. But then I want to find Sn, so Sn is n times T1 plus Tn divided by 2. So it means that if you want to find the sum of the terms from the first one, be careful, not nth terms, not n terms, not in the middle, no. From the first term to the nth term, then you have to add the first term to the last term divided by 2 and multiplied by the number of terms. Yes, or any way that you want to interpret that. Is that understandable? So for example, in this case, the first term is 1, so instead of T1 I have to put 1. The last term is n, so I put n, it becomes n plus 1 times n divided by 2, which is exactly the same formula. But in the book you have another formula, because what happens if I want to write this formula in terms of T1 and D only, then that's also easy. I continue. I write n, instead of T1 I write T1, but instead of Tn I have a formula. This is T1 plus n minus 1d. I think this formula is mainly given in the book. Then T1 plus T1 is 2T1 plus n minus 1d overall divided by 2. Yes? Is that clear? So if we have an arithmetic progression, two formulas are very important for it. One formula is the formula for the general term. So let me write them here. We don't have that much time, at least we can solve some problems. So if we have arithmetic, let me write AP for arithmetic progression, T1, T2, up to Tn and continues. Then we have a formula T sub n is T1 plus n minus 1d. D is the common difference, and Sn, we can write it in two different ways. We can write n times T1 plus Tn divided by 2, or we can write it as n times 2T1 plus n minus 1d divided by 2. So let us keep it somewhere that we can use it today. Okay. I really want to skip the simple problems. Not simple, very simple problems. So I want to skip very simple problems, yes? So example, in any arithmetic progression, so let me write AP for that. In any AP with common difference D, so in any APTN with common difference D, show that D is equal to T sub n minus T sub m divided by n minus m. Of course, n should not be equal to m. Now, these are very simple things. I want you to do them. Yeah, you start working on this. It's very simple. I will write some more for you here. I think we can solve one more and then we continue the lesson next session. But these sequences I will go a little bit fast so that we can reach to arithmetic, so mathematical induction. In a we solve these two problems and we end the lesson today. So let me myself solve the problems. You can help me, of course. This is very simple. In any arithmetic progression Tn with common difference d, we want to show that this formula holds. Yes? So I haven't mentioned which one is the highest term and which one is the lowest term. What we know, of course, m and n are integers, natural numbers, and they are not equal, otherwise the denominator doesn't make sense. And this is an identity you want to prove. I will start from the right-hand side and try to simplify that. So instead of Tn, I can use this formula. So it becomes T1 plus n minus 1d minus, instead of Tm, I write the same thing, but instead of n, I have m. So this becomes T1 plus m minus 1d. And then the denominator, I cannot do anything with that, so it is just n minus m. And then I multiply this negative sign in. What will happen? This becomes negative T1, and this positive T1 will cancel out. Then I will have n minus 1d minus m minus 1d divided by n minus m. And that's a very, very simple exercise, yes? You multiply this in, or I think it's better to factor d out. From this one, n minus 1 is left. From this one, minus m minus 1 is left, divided by n minus m. But if I open this pair of brackets here, it becomes n minus 1 minus m plus 1. This minus 1 and that one are gone. So what is left is n minus m times d, and the denominator is also n minus m. This and that are cancelled, so I get d, and that is the left-hand side. It's very simple. Any questions here? Yeah, very simple. But let us solve that one. Sometimes I think if I am right, if we want to solve this, this is not that helpful just to use the formulas blindly. Yes? So the harder questions for this topic is designed in a way that if you just want to use the formulas blindly, it doesn't work. So how can I solve that problem? In an arithmetic progression, the sum of the first 5 terms is 55. This means S5 is 55. This is guaranteed. But when you write the sum of the last 5 terms is 215, we don't have any notation for the sum of the last 5 terms. Yes? So that is no longer Sn. Sn means the sum of the first n terms. Okay, so it means that you have a sequence, arithmetic progression. If you add the first 5 terms, it is 55. If you go and add the 5 last terms, it is 215. And if you add all the terms, it becomes 351. Okay? First of all, it is clear that this sequence has more than 10 terms. Yes? Because the sum of the first 5 terms is 55. The sum of the last 5 terms is this number. But if I add this number to that number, it becomes 270. But you see that the sum of all the terms is more. So it means that there is something in between. This you need to understand yourself from the problem. So what we have, I don't know. So you have T1 plus, so you don't know how many terms are there. This is the hard part of the problem. You don't know how many terms are there, but we know that, assume that there are n terms. So, and then we continue. The last term, let me call it Tn. The previous term is Tn minus 1. The previous term is n minus 2. Let me put comma. N minus 3, 1, 2, 3, 4, and then Tn minus 4. So I know that if I add these, it becomes what? 55. If I add these, it becomes how much? 215. And if I know that if I add all of them, it becomes 351. This is the situation that I am dealing, yes? The question is to find the value of the first term and the common difference. So how should I do that, do you think? Okay, let me give you a little bit of time to think. I can solve the problem next time. Do you have any idea what to do? So this is the higher level questions. So usually if you just want to use the formulas at the level of Math 5, the normal questions are not that problematic, but you can design some questions that you need to at least think a little bit. Okay, so if you don't mind, let us keep it for the next session. The first thing that I will do next session is to solve this problem. Please think about it. Okay, so let me stop recording the video.